Hello, welcome to Noise Management and its Control. Today is the last day of fourth week of this course, and what we plan to do today is conclude our discussion on transmission line equations. Specifically, we will do one more case for one dimensional waves as they are traveling in straight lines using a Cartesian frame of reference. And here what we will discuss is how do waves travel in an open tube. So, the problem statement is as follows. So, suppose we have an open tube and at one end of the open tube I have a piston, and the piston is moving back and forth and it is generating sound. To measure sound, I have a velocity microphone. So, there are two types of microphones. One microphone is known as a pressure microphone and it measures pressure, and then there are velocity microphones. So, this is a velocity microphone. So, it can measure velocity of the air particles where sound is getting propagated. And then there is the other end of the tube, and the tube is open. So, it is open to the outside larger atmosphere. And what is the pressure outside? It is a very big infinite amount of air is there. So, here the tube opens up into atmosphere. So, the pressure here is P 0, which is atmospheric pressure. So, whatever pressure fluctuations are coming from the tube and they reach the boundary of the tube, they just get dissipated into the overall atmosphere, and the overall, and because this is infinitely large, there are no pressure fluctuations in the outside atmosphere. So, that is the situation. Once again, our coordinate system is such that x is equal to 0 at the open end. This direction is positive and this direction is negative, and the length of the tube is L meters. So, the other end of the tube is x is equal to minus L. Now, my velocity mic is going to measure the velocity of sound waves traveling in the tube, and what it is, when I do the measurements, I find out that the value of velocity at x is equal to minus L is a cosine function, and I can write it as u minus L t, which is velocity at x is equal to minus L, is equal to velocity of the piston, its amplitude times cosine omega t. So, it is a simple function us cosine omega t. So, this is boundary condition at x is equal to minus L. Now, so this is boundary condition x is equal to minus L. So, this is my first boundary condition. The second boundary condition is that the tube is open into the atmosphere. So, whatever pressure fluctuations are there, they do not create any pressure fluctuations on the outside of the tube, which means that, so what that means is, so remember in our one of the earlier lectures we had said that the total pressure when sound travels in atmosphere, P T total pressure is equal to atmospheric pressure, which is constant, plus small changes in pressure, which is small p. So, if the pressure in the atmosphere is fixed and it is not fluctuating, that means that this small p in the atmosphere is 0, which means that a point very close, at a point very close to the boundary, extremely close, at 0 distance to the boundary, the value of p is 0, and from that I can infer that also at just inside the boundary also the pressure fluctuations are 0, which means that a consequence of this open boundary condition is that pressure at x is equal to 0 is 0. So, this is the second boundary condition. So, this is boundary condition number 1, this is boundary condition number 2. So, this is the problem formulation: open tube, velocity at x equals minus L is u s cosine omega t, pressure at x is equal to 0 is 0, and then the question is find p as a function of x and t and u as a function of x and t. So, this is what we have to find. So, once again we start with transmission line equations. So, p of x and t and u of x and t in the matrix form is real of p plus p minus p plus by z naught minus p minus by z naught E minus S x over C E S x over C E S t closed. So, these are the transmission line equations for pressure and velocity, and on the right side of these equations we do not know P plus, we do not know P minus, and we do not know S. So, we have to find, what do we have to find? We have to find P plus, we have to find P minus, and we have to find S. If we know these three things, then I can predict the pressure and velocity at all the points in this tube. At all the points in this tube, I can find pressure and velocity. So, whatever mathematics we are going to do in next 10, 15, 20 minutes, it will be devoted towards figuring out the values of P plus, P minus, and S. Now, in the last two cases, we have done till so far the case for an infinitely long tube, and we have also done the case for a closed tube. And what we found was that the value of S is the complex frequency. Whenever we do the mathematics, it comes to the frequency of the source. So, in this case the frequency of the source is omega. So, it will be that will be the value of S. So, we can say based on that, otherwise we can do all the mathematics and again we will get to the same answer, but just for purpose of brevity we can say that S is equal to j omega, because value of source frequency is omega radians per second. So, right away, but if we do not feel comfortable with right away this kind of a statement, then we can go through all the mathematics which we have described earlier, and we will still come to the conclusion that S is equal to j omega. So, out of P plus, P minus, and S, we have taken care of S. Now, we want to find P plus and P minus, and the way we are going to find out is that we are going to use these two boundary conditions BC1 and BC2, and with this information we will be able to find P plus and P minus. So, now for starters what we will do is we will look at the second boundary condition, which says that at x is equal to 0, which is the open end of the tube, pressure is 0 from BC2. P0t is equal to 0, and let us call this 1a, and let us call this equation 1b. So, from 1a, what do we get? By putting x is equal to 0, we get P of 0t is equal to, so I will number this equation as 2. So, we get P of 0t is equal to real of P plus, and S I am going to put j omega, and x is 0. So, e to the power of minus s x over c, e to the power of s x over c, both of them are 1. So, essentially I get P plus P minus e to the power of j omega t. Okay. So, this is 3, and when I compare 2 and 3, from 2 and 3 we get P plus is equal to minus P minus. So, this is my equation 4. So, now what I do is I rewrite my transmission line equations. So, we will rewrite TL equations. So, what do I have? P x t u x t equals real of P plus, and P minus is negative of P plus. So, it is minus P plus by Z naught e to the power of minus s x over c, and s I know is j omega. So, I say minus j omega x over c e to the power of j omega x over c e to the power of j omega t. So, let us call this equation 5. Actually, I will split it up. I will call this equation as 5a and 5b. So, now in 5a and 5b on the right side, the only thing which I do not know is P plus. So, now we will calculate the value of P plus, and the way we are going to do is we are now going to use our first boundary condition, which is this one, that at x is equal to 0, no, x is equal to minus L, velocity is u s cosine omega t. So, from B C 1 we get velocity at minus L t is equal to u s cosine omega t, and I can express it in exponential format as real of u s e to the power of j omega t. So, this is equation 6, and we can also get the value of velocity at x is equal to minus L from 5b. So, from 5b we get u at minus L t as u minus L t equals real of P plus by Z naught e to the power of minus j omega, and when I put x is equal to minus L, this minus sign goes away. So, this goes away, omega L over C plus e to the power of minus j omega L over C, and then I have e to the power of j omega t. So, this term in bracket is nothing but 2 cosine omega L over C, right. So, what I get is u minus LT is equal to real of P plus by Z naught 2 cosine omega L over C E j omega t. So, this is 7, and when we compare RHS of equation 6 and 7, we get, what do we get? We get real of US E j omega t is equal to real of P plus by Z naught 2 cosine omega L over C E j omega t, which means P plus is what? US times Z naught divided by 2 cosine omega L over C. Okay? And we also know that P minus is minus P plus. So, this is equation 8. And the next thing we do is we put this equation 8, where I have values for P plus and P minus, back into my transmission line equations for pressure and velocity, which is in equation 5. So, putting 8 in 5A and 5B, we get, so first we will write down the expression for pressure. So, pressure, so actually I am not going to do 5B right now, I am just going to do 5A. We get real of P plus. So, what is the equation P plus? So, P plus is US Z naught by 2 cosine omega L over C times e to the power of minus j omega x over C minus P minus, no, plus P minus, and P minus is negative of P plus. So, it is minus US Z naught by 2 cosine omega L over C times E j omega x over C, this entire thing multiplied by E j omega t. So, if I take the common terms out, what I am left with is US Z naught by 2 cosine omega L over C real of E minus j omega x over C minus E j omega x over C E j omega t. Now, what is E minus j omega x over C minus E j omega x over C? This thing. If we go back to our concepts of complex algebra and we do the math, this works out to be minus 2j sine omega x over C. Okay. So, P of x t is, and this 2 cancels out. So, what we are left with is US Z naught by cosine omega L over C times real of minus j sine omega x over C times E j omega t. Now, once again E j omega t is what? It is cosine omega t plus j sine omega t. So, if we substitute this in E j omega t and we take only the real portion of the entire expression, what we are finally left with is u s z naught divided by cosine omega L over c times sine omega x over c sine omega t. Okay. So, this is our expression for pressure, and then now we do similar mathematics for velocity. So, for u of x t we put 8 in 5b, and what do we get? So, we will do the math. So, u of x t equals real of, so the first term is p plus divided by z naught, and p plus is u s divided by times z naught cosine omega L over c, and then I have to divide this by z naught. So, it is this times E minus j omega x over c plus p plus again divided by z naught. So, it is the same term E j omega x, this entire thing multiplied by sine omega t. No, I am sorry, e to the power of j omega t. Okay. So, z naught cancels out and I take all the constant terms, real constant terms outside. So, I am having u s divided by 2 cosine omega L over c real of E minus j omega x by c plus E j omega x by c E j omega t. So, if I do all the math, what I am left with is the equation for velocity is u s by cosine omega L over c times cosine omega x by c cosine omega t. So, this is my expression for velocity, and I will just rewrite my expression for pressure, so that we can look at both of them once again at the same time. So, that is u s times z naught divided by cosine omega L over c sine omega x over c sine omega t. This is the expression for pressure. Couple of things, these once again represent standing waves. The pressure amplitude for the amplitude of the pressure wave is this thing, and it again changes from position to position. The amplitude for velocity is the term encircled in green. Okay. So, this green thing is the velocity envelope. If I plot this thing on an xy plane, then it will give me the velocity envelope. And the red thing is going to give me my pressure envelope. Okay. In case of closed tubes, if you look at the closed tube, the pressure envelope had a value which was maximum at the closed end at x is equal to 0. Here the pressure envelope has a value of 0 at x is equal to 0. So, it is just the opposite. Velocity envelope's value was maximum was minimum at the closed end at x is equal to 0. Here velocity envelope's value when x is equal to 0 is maximum. So, the standing waves are there, but the nature of pressure envelope and the velocity envelope, they just get inversed, right? They just become opposite to each other relative to the closed tube. Last thing I wanted to tell is, if you remember, the impedance for waves in a closed tube were some constant time, were somewhat. It was for closed tube, it was, so impedance closed was a function of x and omega, and if I remember it correctly, it was minus j z naught cotangent omega x over c, right. If you do the same mathematics in open tubes, you will find that z open and how is equal to j z naught tangent of omega x over c. And how do you find these impedances, specific acoustic impedance? By using this relation, z x omega equals complex pressure amplitude divided by complex velocity amplitude. Okay. Now, in case of these waves, what is the complex pressure amplitude? See, what is the complex pressure amplitude? It is this term multiplied by this term, which is same as this thing. Okay. So, it will be u s z naught divided by 2 cosine omega L times minus 2 j sine omega x over c. That is the pressure amplitude, complex pressure amplitude. And when you look at complex velocity amplitude, you get this term multiplied by this, which is cosine omega x over c. Okay. And when you take the ratio, you get this thing. So, once again, I mean, here velocity, so this is what I wanted to talk about standing waves in open tubes. So, overall what we have done over this week is we have developed transmission line equations. Using those transmission line equations, we can now predict how sound travels in straight tubes, and we have also introduced the concept of characteristic impedance, which does not depend on the system, it is a property of the material, and also we have introduced the concept of a specific acoustic impedance, which can be a complex entity. It depends on the system. So, it will have one function for an infinitely long tube, for a closed tube it will be a cotangent function, and for an open tube it will be a tangent function. And with this we conclude our discussion for today. Next week we will discuss similar ways, but in a spherical frame of reference, and with that discussion we will proceed into the next phase of this course, where we will start talking about noise, noise measurement, noise characterization, and solving noise related problems. So, with that we close our discussion. Thank you and have a great weekend.